Good morning, Berkeley. Buonasera, Europe. 晚上好, Asia. My name is Ting Lin. I'm here, very excited to be here today, sharing with you guidelines on utilization of simulated ground motions for engineering building response applications. I'm presenting today on behalf of a task committee at SCAD Ground Motion Simulation Validation Technical Activity Group. And currently, I direct the multi-hazard sustainability research group at Texas Tech University. Last time I was here at Peer was 9 years ago. So I'm very, very honored to be here again to share this topic that have been dear and near to me for the past decade or so. So where it all began, 2012, Mars rover landing, Curiosity. Everything begins with questions and challenges. So right off when I got my PhD from Northern California on topics related to PSHA and PBE, Southern California presented the Raptors challenge. A trip to Southern California Earthquake Center SCAD inspired me with geophysics and computer science. So why not probabilistic plus physics-based? Not just for the hazard, but also for risk. Why not be the guinea pig of cybershake? So essentially, we can use the strength of one field to solve a tough problem of another. Long period simulations for tall buildings in the Pacific Rim. So this is a doodle I drew back in 2012, thinking how we could integrate the strength of various areas, structural engineering, geophysics, and high-performance computing. So essentially, we could get advances from physics-based simulations for the long period portion, and then maybe together with stochastic simulations for the short period or high-frequency portion, and then having them together simulated broadband ground motions for potentially engineering usage to supplement traditional empirical recorded ground motion database to form a combined database. So we could then still be using the same thing like this ground motion selection algorithms, for instance, to match some efficient and sufficient intensity measures. So for instance, we could expand from amplitude to duration to some new features such as those from basin. So this is when SCAD comes in. Over the years, we're very fortunate to serve as PI and co-PI on a number of SCAD projects. So the focus for today would be the last one, 173, but the work before that led to some of the guidelines and recommendations we're going to share today. And part of it is basically seeing the beauty of cybershake, how the physics-based and probabilistic work can come together. So essentially, it's just the PSHA, but then having the physics-based on top of it. So if we propagate that from the hazard portion to risk, then we could complete the end-to-end analysis. So in other words, we could go from fault rupture, the wave propagation to ground motions, examine the waveforms, and then going into more the pure type of framework in terms of looking at some of the intensity measures, whatnot, and engineering demand parameters all the way, structural responses all the way to collapse, for instance. But that means high performance computing is required. So back then, we saw earthquake engineers were using a relatively smaller number of ground motions to run nonlinear dynamic analysis. But then in this earth science world, essentially a lot of computing power were already used. So I thought, why not apply for XC startup award? So we were lucky to get one of those back in 2013 to get 200,000 supercomputing hours a year back at Tech, the Stampede 1 back then, to run some of those analyses. So that essentially speed up a lot of earthquake engineering research and provide the space for us to explore much more. So in other words, a lot of the high performance computing that will enable us to run the end-to-end analysis. And once we get that, then we got a rich database, not just from the ground motion, but also from the response, so that we can start mining data. So it's essentially combining the beauty of HPC and machine learning to push it to the next level. like a small thought in the basin, then in big waves into motion, like how a single girl can make discovery open. So sometimes it's just that one single goal, that one idea that led to another, That's so exciting. So here's the research team. This research is supported by SCET 173, funded by NSF and USGS cooperative agreements. And I'm the PI, alongside fearless ground motion simulation validation group leaders, Sanas, Rezian, and Nicholas Rugo from USGS, and then Greg, Diana, Jack Baker from Stanford, and Fazil Zaran from UC Irvine. And also like to acknowledge the PhD students here, Nana Yalich and Guangshi Zhong, both are now doctors. And of course, this work is impossible without a lot of people at SCET, including John Stewart, Christine Goulet, Rob Graves, Phil Macklin, C.B. Krause, John Hayes, practicing engineers as well, computer scientists, Fabio Silva, Scott Callahan, Kevin Milner, Sylvia Mazzoni, Edric Polk, Chan Hong, and then overall the SCET seismology and IT computer science and special project team and the ground motion simulation validation workshop participants. We thank them for their valuable contributions. So overall, why? The question overall, what is the topic here? So essentially, we know ground motion selection has been there for a long time and it's important for structural response, characterization, and then there's also more and more use in tall buildings and also other structures. And then there are already some standards out there, for instance, ASTM 716, FEMA P58, Pure TBI, LATBSDC, along of several others. And essentially, we'll look at target response spectra such as uniform hazard, risk target, or conditional spectra. And then because essentially we would rely traditionally because of the limited number of motions that are recorded motions in the database. So we need to kind of do some modifications such as amplitude scaling or spectral matching, and sometimes that could introduce bias in structural response. And at the same time, sometimes we're basically using, let's say, earthquakes from Chichi earthquake to analyze structures that are located very far away from where that earthquake is coming from. And because of the increasing availability and refinement of simulated motions, and yesterday we heard great talks also from some of the authors here, like say Maya and Baroza, Graves, Pitaka, Taboda, et al. And now it becomes much more viable option for regular set of circumstances. So the goal here is then essentially kind of going from just research work kind of happily in our own real academic work to maybe broader adoption in the practicing community. And so we might ask also why, what is the benefit of ground motions, simulated ground motion? We've been using recorded motions for a long time, why the switch? So part of this is essentially ground motion simulations are very useful for especially large magnitude and close distance events. For instance, if you go to PRNGA database, you store the distribution of magnitude distances, but very rarely we see the large magnitude and close distance, which are of most importance, especially if we're looking at, let's say, tall buildings in downtown areas in San Francisco, Los Angeles, and many other major cities around the world. Another one, if you just kind of also view it purely from ground motion database point of view, then here we could see just one single site from Los Angeles downtown from cyber shade simulations by Graves et al. 2011, and specific number of studies 15.12 alone will have much larger coverage at various hazard levels. So from 50% in 21 years to 1% in 200 years, probably enough for a lot of the engineering, either research or practice applications. So essentially, that's the beauty. So essentially, we could then use this rich ground motion database, simulated ones, to explore how a building is going to respond. And then also, I'd like to highlight that the simulations here, so both broadband platform, Macklin et al. 2015, and study number 17, version number 17.3, and also CyberShade 15.12 are actually the results of interaction between ground motion modelers and engineering users. So essentially a lot of this, for instance, earthquake scenario being simulated, the 17.3 was specifically simulated because of the need for those motions in places like San Francisco downtown. And then the broadband component was specifically added thanks to SCAD computational team and seismologists, because we are interested not just in the long period portion of the ground motions, but also for high frequency content that will be important for some of the responses as well. And then also we realized a lot of this generated for site-specific extent, and so we would like to demonstrate here, for instance, get PPP 17.3 scenario simulations here. So essentially, we got 3 sites. So the idea here is very similar to back in the days when we're thinking about just the hazard port. When I selected, for instance, Seattle, Stanford, and BSO to represent different kinds of scenarios that could be broadened to our larger context. And this is the same idea. So essentially, we got San Francisco downtown, where we don't really have the motions for, and then that's why, thanks to upgrades to kind of basically generated all of this. And then the downtown Los Angeles area also, plus another one, San Bernardino or Nordic one in the Los Angeles basin. So those 2 later sites also are co-located with Cybershape as well. So essentially that enables us to compare broadband platform simulations, Cybershape simulations, and then also push basically the whole range. And you see those are kind of coming from several major contributing fault systems. And this is a group effort with many listed here. So then we go into validation. So very often we talk about from the ground motion database point of view, we don't have those, so that's why we need simulation. But it's also important from a physics-based perspective too, because some of the site-specific non-ergodic conditions, for instance, sedimentary basins, Thompson Wall, 2016, Mostretti et al., 2018 may not be fully captured in some of those traditional GMPs. So then that's the value also of physics-based simulated motions. And the other piece of this is, well, some of the older generations of EVP, earlier versions, require some degree of scaling, and this is an extensive ground motion simulation validation effort by the group, many in the past, validating from hazard to risk related BPP. It still needs a little bit of scaling. Cybershape, though, because it's so large and also throwing the probabilistic piece in it too, then basically you can just use unscaled site-specific simulations. And then we can also think about not just the traditional PBE while you go rely on IM, EDP. Now we can sidestep IM too, because we could basically go from form directly to structure. And then in between, we're free to explore anything in between. So I'd like to kind of walk through some of this. That initial random idea of why not a long period, and then perseverance over the years led to essentially the ground motion simulation validation of tall buildings. So essentially we started with something very similar to so the original approach of ground motion selection, and then look at what if we have similar intensity measure, and what if we can compare maybe a broadband platform versus record motions, and we can look at intensity measures like spectral shape, duration, whatnot. Essentially, it's relatively close, and any discrepancy, we can also trace them back to assay correlations, which I think Jeff also talked about in the later on in the from different angle. And then another piece is the Cybershape. Essentially, we can bypass IM, that whole exploration space. So we can then look at conventional versus Cybershape. So conventional being that you can use the USGS hazard and then PRNGA database for ground motions, versus Cybershape where you use a hazard and ground motions both from Cybershape. And essentially, we can then also compare them in terms of the annual rate of exceedance of EDPs and see how they look like. And from there, we can also characterize basin effects as well. And then we kind of can cover several aspects of this. For instance, we first look at Los Angeles downtown, and there's about 500,000 ground motions. So we did that about 500,000 nonlinear response history analysis there to see how they look like. And results are fairly close. Any discrepancy basically could trace back to the differences in the hazards generated from USGS versus Cybershape. But then that's too happy of a result, so we were not too happy about that. That's just as expected. So we wanted to really push the limit. Say, why not go to something, the deepest basin, for instance, STNI in LA Basin, to see how that performs. And sure enough, discrepancy happens. So then, how are we going to explore? So there we see differences, but why? So the beauty of simulated motions essentially we can look at basically what among those motions, which one caused tall building collapse, which one did not. So kind of delineated with those dots here, blue ones being all, and all the collapse versus non-collapse. And then also we can look into what contributes to those. So in other words, we can then do not just the hazard derivation, which is traditional USGS approach. You can get that from USGS hazard web interface. We can also do risk deaggregation as well. So in other words, we can also do what other motions that cause collapse, and also look into what is the magnitude distance distribution from those. But furthermore, because of this whole range of rupture wave propagation and the waveforms and everything, so we can even trace them back to the faults that were contributing to those. And then from there, we could look into, based on those insights, we could form archetypes to represent some of the features that really are damaging. And here we call them long period cyclic, so LPC in short. That's kind of characteristic of basin. And then you could also do like pulse-like motion, long period cyclic motion, and then we could do combination permutation, pretty much single, multiple, one plus another, and then whatnot. And then we can also look into those that we're familiar with. For instance, if we just match the spectral shape, we match the duration, everything's the same. But the only difference is one set of motions will come from basin, the other one coming from non-basin, and sure enough, the basin ones are more than damaging. So we can then look into what really is the root cause of this. And that's where new IMs are proposed. Duration and sustained amplitude adjusted spectral RSX in short. So in other words, traditional IM like spectral acceleration essentially is the first peak. But if you have cyclic motions, then you could then count what is the, for instance, here, highlight here, the fifth peak instead of the first peak. And that's where we see differences from basin versus non-basin motions. And then we can then push it further into, let's say, what if we want to look at collapse classification? Then we could do model selection using different IMs as predictors, and we can then utilize techniques in machine learning to look at what are some of those really results in a good precision recall curve, for instance. And then using that, we can then populate this into regional analysis. So in other words, then once you have the database of 2 million also responses that we already obtain full nonlinear response results from, then we can use those to train the data, and then we can then populate them all across more than 300 sites in Cybershape's Los Angeles Basin area. And then you can then plot, for instance, collapse risk. And this could then be extended. You can think about sort of like the different site and building combinations and in different settings, different locations. And going to utilizations, because of this large number of ground motions, such as those for just illustrated Cybershape and broadband platform, so we can then investigate this kind of relationship between all the IAMs, your EDPs, and everything in between. And then some of this later were also, for instance, Baker also looking into the Cybershape 1512 ground motion selection for engineer analysis, and then Fayaz also looking into extension of this tall building analysis to ordinary bridges. So in other words, we now have a group of people who are interested in utilizing Cybershape for broader use. And then we will also look into—
You have 1 minute.
Okay. We'll also look into structural responses in terms of some of the back to the traditional ones. Let's say code-based versus performance-based. So in other words, we could also follow code-based procedure and ASC procedure, and we found that simulations actually are more consistent with governing hazard, including a better match with target duration, even if we don't explicitly match for that. And then also for purpose-based engineering, we also look at the results are mostly similar, except for basin and near fault sites. And then with cases where, for instance, LADT that's dominated by multiple contributing earthquakes, they can look into ground motion selection based on source-specific target. So here's a list of recommendations. Simulation for seismic environment of interest, and then also should be valid for engineering application of interest, and then should cover the realistic energy covering the whole frequency of excitation, and then also duration of other metrics like basin features. If they're important, they would need to be incorporated into simulations, and if you need components, those should also be incorporated. And then side effects could be also huge too, and a nonlinear side response as well. And for instance, some of the near surface geotechnical layer could also be very important. And here are some additional data resources. And here comes back to our earthquake song, science engineering. So Perseverance. Now 2021, Mars, another Mars rover landing. I say just keep doing the next red things. Introduction, motivation, simulation, validation, utilization, recommendations. Who knows what's next? Thank you all for your attention.